Okay, so this is a continuation video from our last video. So in this video, we would now be once again calculating for the bending stress, but this time we would now be making use of this particular moment at the bottom or at the middle. So let us now solve for the actual bending stress of this particular beam if the moment is now 68 kilonewton meter. So once again, if our moment is now equal to 68 kilonewton meter, so let us now solve for the bending stress. Okay, so how can we do that? So once again, from the previous video that we had, what we did was that we have solved for the cracking moment first. Then we have compared it with the actual moment if it would crack or not. So I would not resolve for the cracking moment here since we still are making use of the same section as with the last time. So once again, our cracked moment or the cracked moment I should say is equal to 28.767. So as per solved for in the last video. So once again, our cracking moment is equal to, so what was that again? That is 28.767. So as a recap, MCR is equal to F sub R times IG over YT. And that FR is equal to 0.62 lambda times square root of F prime C. So if you want the detailed solution for this, better watch the previous video. Anyway, so once again, the only use of this cracking moment is in order for us to know if this particular moment here would cause cracking. So as you can see that since our moment, so this moment is now, or the actual moment I should say, of 68 kilonewton meter is now greater than our cracked moment, which is MCR of 28.767, meaning that our section would now crack. So this is now considered as a cracked section. So what does a cracked section look like in theory? So once again, from our previous video, I have already shown you this particular section. Whereas, suppose that this is now the neutral axis. If this is the neutral axis, everything above it, if this is experiencing positive moment, everything above it will now be under compression, and everything below the neutral axis is now under tension. So take note that this is if the beam is experiencing positive moment. If it is experiencing negative moment, it means that fibers on top will now be considered tension members or tension fibers, and the fibers below would now be experiencing compression. Okay, but once again, in our example, it is assumed that it is experiencing positive moment. Okay, so once again, since our section is cracked, meaning that it has um it has ang hirap pag English, mas mataas na ngayon yung stress dito kaysa sa FR since it has already cracked. So meaning that we are now to assume that this part of the concrete here is already destroyed and thus will not help in our beam. So that is our assumption for our analysis, okay? So once again, if our section is cracked, we are now to assume that all of the tension fibers or all of the concrete fibers at the tension side will now be destroyed already. Let us assume it that way. But take note that we still have our rebars here. So with that being said, guys, for cracked section, the rebars here would be the ones that would carry all of the tensile loads. Okay, and as you can see, guys, that in our section here, it is not gross, of course, since it has already cracked, meaning that the moment of inertia that we will be making use is the cracked moment of inertia. Okay, so how can we solve for this here? So let me erase this first. So take note that our formula is still MC over I. It is just that for our I, we will now be making use of the cracked moment of inertia. But take note, according to elastic theory, that in order for you to solve for this particular bending stress making use of MC over I, our figure or our problem, or let's say the figure that we are considering, must be homogeneous. When we say homogeneous, they must have the same material, okay? Or let's say it kind of must be prismatic in a way. Anyway, so as you can see, this is concrete here, and this one at the bottom is steel. And as you know, that both of them are, have different materials. So concrete is of course different from steel. And we know that steel is stronger than concrete. With that being said, with this alone, we cannot make use of this equation. So in order for us to make use of this equation, we must first convert this section into its equivalent area. So from that, guys, what I mean here is that I would now be converting our steel section or steel rebars into its equivalent concrete area. So from that, guys, it would now look like this. So this is still the concrete area. And for the steel area, it would now look like this. So this is now the equivalent concrete area for that steel. So what is implied here is that it takes this much concrete to replace this much rebars. Okay, so how can we know this particular area here? So suppose that this is now AS, or the area of steel. So for the area of steel, that is basically the total area of these circular rebars here. So we would just be multiplying it by the value N. What is the value N? The value N is equal to the modular ratio. Okay? So for the modular ratio N is equal to the ratio of their modulus of elasticity. Okay? So if you would be dividing the modulus of elasticity of steel divided by the modulus of elasticity of concrete, so that is now basically your modular ratio. Okay. So furthermore, so once again, this is now equal to modulus of elasticity of steel divided by the modulus of elasticity of concrete. So the modulus of elasticity of steel, according to the code, is equal to 200 gigapascals or 200,000 megapascal. Okay, so what about for the modulus of elasticity of concrete? So if you are to look at the code, it is actually given here. So if you are making use of normal weight concrete, so for normal weight concrete, meaning that the modulus of elasticity that you will be making use is equal to 4,700 times square root of F prime C. So as you can see, that it is dependent upon its compressive strength. So once again, this is equal to 4,700 times the square root of F prime C, or the square root of 21, if I am right. So our compressive strength is 21. Okay, so from that, guys, our N is now equal to 200,000 divided by 4,700 times square root of F prime C, or FC prime. Okay, so solving for this value, looking once again at the calculator to your left. So 200,000 megapascal. So let me write 200,000 divided by 4,700 times the square root of 21. So once again, this should be 21. Okay, so with that, the modular ratio is now equal to 9.29, 9.28. So 9.29. So 200,000 times. Okay. So according to the code, guys, for the modular ratio, so take note, this is a code provision according to NCP. So for the modular ratio, the value of N, or the modular ratio, must always be greater than or equal to 6. Okay. So as you can see that our value is greater than 6, meaning that we will be making use of this value. But for instances or for the event that the value of your modular ratio is, let's say, equal to 5 or maybe 4, the value of the modular ratio that you will be making use is 6. Okay, so this is now the minimum value for the modular ratio. Okay, so furthermore, another code provision is that the value of n must be rounded to the nearest whole value. So to be honest with you guys, I do not really know the rationale of this, because if you would be asking me, wouldn't it be accurate if I would be making use of this value? So yes, that might be true, but according to the code provision, we must be rounding them to the nearest whole value. Okay, so with that, guys, the nearest whole value here is 9. So meaning, guys, that our value for n is now equal to 9. Okay, so going back here, so if I am now to, let's say, continue here, once again, this is now our crack section. So here. So if this is now, oops, sorry. So if this is our crack section and transform section, once again, this is now our transformed section. Okay, so the value of the breadth of the beam is still 350. Wait, am I correct? 300, I should say. So the value is 300 mm. And the value of this particular area, so the equivalent area of steel is now equal to 9 times what is now the area of steel. So the area of steel, since according to the problem, we have 3 pieces of 28 mm diameter rebar. So meaning, guys, that for the area, since we have 3 pieces of diameter 28, what's that, 28? So 28 mm diameter rebars, we would just be solving for the area of 1 rebar and just multiply it by 3. So the area of 1 rebar is pi over 4 times diameter squared, so that is 28 mm squared, times 3. Okay, so from that, looking at the calculator once again, so this is now equal to 9 times 3 times pi over 4 times 28 squared. So 9 times 3 times pi over 4 times 28 squared. So this is now equal to 16625.308 millimeter squared. Okay, so once again, let me remind you that this distance here, so where should I draw? So the distance from the top compression fiber up until the centroid of the rebar is now equal to 385 mm as seen here. So once again, this is 385. Okay, so now as you can see here that we still have a missing dimension. So what is this particular dimension? So once again, what is this? So let us now name this as x. So if you are thinking, if previously we have said that the neutral axis is located at the middle, then if you are thinking that this should be 225 mm, then actually you are wrong. So that is not really the case here, since our section has already cracked. So in order for us to solve for this value, we will now be making use of Varignon's theorem. And from that, guys, we are now to say that this here should be the centroid. Okay? So since this is now our neutral axis, as said here, if this is now our neutral axis, it means that that should be the location of the centroid of our beam, with this being taken into consideration. So as a shortcut for our Varignon's theorem, we can now get the moment about this point going here and from this point going here. So what I mean here is that let us first consider the concrete section here. So from that, the total area of that concrete section is now equal to, so wait, Varinian's theorem. So Varinian's theorem. So for the area here, so that is now equal to 300 times x. Okay, so once again, if this is now my reference point, what is now the lever arm of that particular area? So that is now equal to, so if this is its centroid, meaning that this is equal to x over 2. So this is now the lever arm. So area divided by, area times lever arm, I should say. So this is now equal to, so the area of the steel, which is 16625.308 millimeters squared. So take note that you should make use of the transformed section of the steel times the lever arm. So in this case, our lever arm is 385 minus x. Okay? So from that, this is now equal to 385 minus x. So why? Because this should be the lever arm. Okay? So this is now the lever arm. And from that, if this is 385 and this is x, meaning that this dimension here should be equal to 385 minus x. Thus, this equation. So you can make use of the shift solve feature of your calculator. However, since we are now to deal with a quadratic equation, there are actually two possible answers. And if you would be making use of shift solve, there is also a chance that the value that your calculator will show you is the incorrect one. So what I mean here is that, for example, I would first solve for this value here in terms of quadratic equation, or making use of mode 5 then 3 for quadratic equation. So what I would be doing is that I will be rearranging this formula in this format. So for the third one here, so this one here, okay? So from that, this is now equal to, this is 150 x squared. So once again, what I did here was that I have simplified this. So times or plus. So if I would be multiplying 16625.308, 308 I should say, times negative 6, and I will be transferring it to the other side. So meaning that it is now positive 16625.308 millimeters squared x times, or plus I should say. So if you would now be multiplying 16625.308 times positive 385, and I will be transposing them to the other side, meaning that this should be negative already. So the value of it would now be equal to, so mode. So for a moment, so this should be equal to, so 16625.308 times 385. So this is now equal to 6400743.58. So this is now equal to 0. So from that, I can now say that this is my value A, B, and C. If I would now make use of mode 5, 3. So once again, I would just be typing them here. So 150. This is also 16625.308. And this is negative 6400743.58. Okay, so our answer here, so for x1, for the first answer here, that is equal to 158.458 millimeters. Then for the second one, our answer here is negative 269.293 mm. But take note, guys, our answer here would now be the realistic one, which is the positive one, since we cannot have a negative value of x. Okay, so once again, we have two answers here. But what if we would be solving for this equation using shift solve? So looking at the calculator to your left, so I would just be writing our original equation here. So from that, that is 300 times alpha x squared divided by 2. This is now equal to 16625.308 times 385 minus alpha x. Okay. So there is actually a 50-50 chance that No, actually it is not 50-50, but there is a chance that your answer or the answer that it would display is this value here or this value here. So upon pressing, oops, sorry, it should be shift solve. So if I am now to solve for it via shift solve method, solving for x, so for by coincidence that the answer here is now the correct one. Okay, so take note that when your calculator is solving for anything, it is not actually solving if you would now be solving for shift solve. What happens here is that your calculator would now guess for a value. Then from that, if let's say its guessed value would now give him or the calculator an equation that is true, it means that, for example, that if your calculator has guessed this number, and if it would now substitute it to this equation, and if it would prove to be true, then it would now display that. But if I am now, let's say, to type shift solve, then I would now be writing an answer here, let's say I would now tell the calculator to start guessing from the negative 200 value. It means that it would now display this particular value. Okay, so it would be better if you would now be making use of this equation and make use of mode 5 do, or if you really want to make use of the shift solve method, make sure that if let's say that the what you call this, the value that is being displayed by your calculator is incorrect or illogical, so just shift solve once again, then type any random positive number. So for example, I would now be typing, let's say, so if I would be typing 158, of course it would now arrive at this particular answer, since 158.458 is nearer than 148 than negative 269. But take note that, for example, we still do not know this answer. You can just guess for a number that is high. So let's say solve for value of x using 500. So as you can see, it has already displayed this. Okay, so daming dada. Next tayo dito. Okay, so once again, our value of x is now equal to 158. So if I am to redraw them here, so this is now the section. Once again, this is still 385. So this is 385. This is 300. And this is now 158.458 mm. And as for this is now NAS. And NAS, according to our previous solution, that is 16625.308. So 16625.308. Okay, so since you already know this value, the next thing that we should solve for is the cracked moment of inertia. Okay, so what about for cracked moment of inertia? What do we do here? So for the cracked moment of inertia, what we must do here is that we should solve for the moment of inertia about the neutral axis, and this is the neutral axis. So if you are thinking, okay, so for example, that for the cracked moment of inertia, this is now equal to, once again, it should be in reference to this axis here. So let me redraw it. So if this here, if this is 158.458, if you would be solving for the moment of inertia there by 1/12 times BH cube, which is 308, or let's say I would just be typing them here, so plus B times x cube. Take note that if you would be making use of this formula, you are actually solving for the moment of inertia about its centroid. And from that, you must first transfer it to this location via transfer formula, and from that, this is now equal to plus x. So what, sorry. For the transfer formula, that is actually equal to AD squared, where A is equal to the total area times D. D is the distance from its centroid to the axis that you are analyzing. And once again, we should analyze our beams in the neutral axis. So from that, this is now equal to 300, sorry, the area. So once again, AD squared. So our area is equal to B times X. And from that, B times X is now equal to, or sorry, the distance from this point to this point is basically equal to X over 2. So times X over 2. And from that, guys, this is actually equal to, so 1 over 12 times bx cubed. Oh, sorry, this should be squared, I should say, since d squared. Anyway, so plus, this is now equal to bx cubed over, so 2 squared, this is now bx over 4. So if you would be further simplifying this, looking at the calculator to your left, so 1 over 12, 1 over 12 plus 1/4, that is actually equal to 1/3. So 1 over 3 bx cubed. Okay. So you can either make use of this equation or just the derived equation, 1/3 bx cubed. Okay, so that is for the moment of inertia of this particular value. But what about for our steel section here? So since we do not know what the value of B is, and we do not know what the value of our H is, we can just transfer the total area to this location. So from that, just add. So add AD squared once again. So its area is equal to N times AS. And the distance squared, or the transfer distance, would now be equal to, once again, if this is X, this is 385 minus X. Or if this is now equal to the depth, generally speaking, this is basically depth minus X. But in our case, that is 385 minus 158.458. But I just want to derive our equation here, so that if you do not want to memorize this particular equation, you can memorize a much lesser one, or a rather much shorter one. So once again, from that, this is now equal to D minus X squared. Okay, so from that, this is now our formula for the cracked moment of inertia. Okay, so ito po. So ICR is equal to 1/3 bx cubed times, plus NAS times D minus X. So from that, our cracked moment of inertia is now equal to, so 1/3 times B, and our B is equal to 300. Our X, as solved for earlier, is equal to 158.458. Sorry, 458, I should say. Cube plus NAS. So the value of our NAS, we have already solved for it earlier, which is 16625.308 times D minus X squared. So that is now equal to, so our D is equal to 385. So 385 minus X. So the value of X, I should say, is once again 158.458. So 158.458 quantity squared. So from that, the moment of inertia, or the cracked moment of inertia, is now equal to, so looking at the calculator to your right once again, so 1/3 times 300 times 158.458 cube, so cube, plus 16625.308 times 385 minus 158.458 squared. Okay. So from that, our answer here is 1251103.256 millimeter raised to 4. And it would be better if you would be storing this value to an unused variable in our calculator, in order for us not to type this from time to time. So what I would be doing is that I would be storing this to A. Okay, so from that, guys, this is now equal to, so I will be shift storing it to A. So from that, guys, I would just be making use of A for our cracked moment of inertia. So since we already know the crack moment of inertia, we can now solve for the actual bending stress. So for FB, this is now equal to, so let us now solve for the concrete first, or the compression concrete. Once again, looking at this value, let us solve for the extreme fiber here. Okay, so from that, MC over I, for our M, what was the M once again? I think the M was 68. So from that, 68 kilonewton meter. But once again, since it is still in kilonewton meter, multiply this by 1 million in order for it to be converted into Newton millimeter. So M times C. So the value of C is the distance once again from the neutral axis up until the furthest compression fiber. And in this case, guys, if this is the neutral axis and this is the furthest compression fiber, it means that the value of C that we will be making use is 158.458. So from that, this is now equal to 158.458 millimeters divided by the crack moment of inertia, and in that case, that is ICR. And since we have stored it to A, so let us just make use of A. So from that, the FB of concrete is now equal to, so 68 times 10 raised to 6 times 158.458 divided by alpha A. Our answer here is now equal to 8.613 megapascal. Okay, so that is now the bending stress of concrete. Okay, so for the bending stress of steel, so we have a catch here. So for FB steel, if you can remember, guys, that for our MC over ICR, we have converted our steel member into its equivalent concrete area. So what we would be doing here, that for its stress, we would also be multiplying it by the value of N. Okay? So from that, for FB of steel, this is now equal to, so the moment is equal to, so let me rewrite my ugly writing. So again, for FB steel, this is now equal to, our moment is still 68. Am I correct? 68, okay. 68 times 10 raised to 6 times the value of C, and the value of C is now equal to, so in this case, the value of C must be the distance from the neutral axis up until the centroid of the rebars, and that is D minus 6. So from that, our D is 385 minus X, and our X is 15, what was that again? 158.458. Okay, so we would be dividing this by ICR, and since we have stored it in A, so times A times N, okay? So do not forget to multiply this by the modular ratio in order for you to convert it back to steel once again. Okay, so from that, the bending stress of steel is now equal to, looking at the calculator to your left, so 68 times 10 raised to 6 times 385 minus 158.458 divided by A. Okay, so our answer here is 12.31, but if you would be multiplying it by 9, so just multiply it by 9, so the stress by the steel is 110.817 megapascal. Okay, so that is how you would be solving for the actual stresses of these steels. Okay, so there.